So we're talking about spontaneous reactions, and now we introduced a new concept, which is in addition to being exergonic, to be spontaneous, we also have to worry about how long it actually takes the reaction to go. A reaction can be very exergonic or very exothermic, but still take such a long time to go that we think it's not happening at all. So we need to introduce a new way of characterizing reactions in addition to the thermodynamics. And so we introduce this concept of a reaction rate, and more specifically, a reaction rate constant. So measuring how fast reactions go, how long it takes them to finish, is a really important part of chemistry, an important way of connecting to understanding how reactions actually work. And so these rates of reactions are characterized in terms of this thing called a rate constant. Real reactions have rates that cover many, many orders of magnitude. There are reactions which are so slow, take place in a geological timescale, millions of years. And on the other hand, there are some reactions which are so fast that they occur in less than a trillionth of a second. You can't even see them go, they're so fast. There's an enormous change and range, in reaction rates and correspondingly in reaction rate constants. The rate of reaction, or the rate constant, is determined by the activation energy. We learned about that in the previous video. So that's basically telling us how much energy is required to make the reaction go. So what really determines the rate of the reaction rate constant is how much energy is required versus how much energy the system has. And the energy the system has that it can use isn't the internal energy, isn't the potential energy, it's the kinetic energy. So it's how much kinetic energy the system has. That's how much you can use. And so it's a balance between how much do I have that I can use versus how much do I need. So we can write the rate constant of reactions, an equation for it. We're going to go just straight to the equation. We're not going to derive this equation. So let's have a look at how this works. So rate constant is normally given the symbol lowercase k. There it is, rate constant. And it has units. And this isn't rate of reaction. This isn't a time scale of reaction. It's in time. It's rate, which means something per time. So the units are per time, and very often seconds to -1 is given. So in other words, per second. So how many reactions or how many molecules react per second. That's the rate, and the rate constant connects to that. So obviously it depends upon the activation energy, and that is the energy which is required. We need that energy to make the reaction go. And the kinetic energy we have, we can calculate that. We've seen this before as by the product of the gas constant and the temperature. So this is the available thermal energy. We call this thermal energy. And it's really kinetic energy, isn't it? So it's a balance between the energy required and the energy that we have. And there's an exponent into, there's a negative exponent. And so we can see from this that the larger the energy required is. If this is larger, this is going to make the rate constant smaller. Correspondingly, if the available thermal energy is larger, this is going to make the available rate constant larger. The available rate constant larger. So larger energy required, reaction slows down. Larger available thermal energy, reaction speeds up. There's another thing here, another part of the equation. It's a bunch of constants. They don't change. Well, temperature isn't there. So, but at constant temperature, these are constants. These constants evaluate to about 10 to the 13 per second. And so this is also a rate as well. We don't really have time, and it's not really the appropriate in the scope of this course to explain exactly where all those constants come from. We'll talk about a little bit more on those in a second, but the important point is they evaluate to something like 10 to the 13 or something like this. So this is a rather important equation. This tells us the larger the delta G, the smaller the rate constant, the slower the reaction, and the larger the temperature, the larger AT, the larger the rate constant, the faster the reaction. So just as when we study energetics, of a chemical reaction. That field has a name. That's called thermodynamics. The study of the factors that control the time scales or the rates of reactions also has a name. This is called kinetics. So now we realize we have to take thermodynamic factors into account and also kinetic factors into account. We want to understand what makes reactions go, and now what makes them go in a reasonable timescale. So like I say, the rate constant as units of reciprocal time, often seconds to the -1, although it could be hours or even years to the -1, I guess. And it gives information about how many reactions occur or molecules react per unit time per second. And so the smaller the rate constant, the longer time it takes to complete a reaction. Like I say, it also depends upon these constants. Again, we're not going to get into detail where these constants come from, except that they evaluate roughly 10 to the 13 per second. This is a different kind of K here, unfortunately. It's called the Boltzmann constant, and H is the Planck constant. You don't need to know any of this stuff, but you just need to understand how what their role is in making the equation work. So we can sort of see what's happening. So if this exponent term includes the energy, if it was very small, then the rate constant would basically be 10 to the 13. And that's very small if the energy required was very small, or even, how about 0? If there wasn't any activation energy at all, then the rate constant would be about 10 to the 13. That's a lot, right? 10 to the 13 thick chemical reactions per second. That's an awful lot. That's a very fast reaction. So what we have a little table here which sort of tries to illustrate a point about how, now using this equation, we can figure out really how does this energy required, this activation energy, how does it really affect how fast the reaction goes, and if you like, the time scale of the reaction. So here's a little table, and we've calculated rate constants in per second for different values of the activation energy, starting with no activation energy at all. It's really hard to find any reaction with just no activation energy at all, right? There are almost none. In fact, I can only think of maybe one, and that's one we discovered in our lab, actually, by coincidence. So if there's no activation at all, then the rate constant will be about 10 to the 13. It's a very large number, and the time for the reaction is the reciprocal of that. And so the time for this reaction to occur would be 10 to the minus 13 seconds, which is 3 times 10 to the minus 21 years. This is a really fast reaction, obviously. And so now we repeated that calculation for you. You don't have to know any of these numbers, obviously. Don't memorize any of this stuff. For different values of the activation energy, increasing this direction. So these are increasing Gibbs activation energies. And as the activation energy starts to get large, the rate constant starts to get small, in a hurry. And the time scale for the reaction also gets very large in a hurry. So by the time we're at about 80 kilojoules per mole, the rate constant's gone from 10 to the 13 to 0.095 seconds to -1. And instead of reaction taking 10 to minus 13 seconds, now it takes 10 seconds to occur. You could watch that reaction actually occurring. And by the time we get very large, like 180 or 100, then the rate constant is very, very small. The time scales of the reaction are very large. We're talking about 3 times 10 to the 14 years for an activation Gibbs energy of 200 kilojoules per mole. So that reaction is so slow, it's going to look like it has stopped. And that's the situation we have for some of these reactions that look like they don't go. They have very large activation Gibbs energies, and according to our rate constant equation here, we can calculate the rate constant and therefore what the time scale for the reaction should be, and they're years and years and years and years and years. So this is why these reactions seem to have actually stopped.